All right, good morning, everybody. I have just hit the broadcast button, so we have officially begun, but I'm going to wait a few minutes to really start to let people join in here. I see some attendees showing up, so that's great. I hope some of you had a chance to attend a related tutorial on Friday. I actually borrowed one of their slides that I'll include in this presentation, so there'll be some continuity of theme between that tutorial and this tutorial. All right, so people are coming in now, and I'm just going to just wait a minute or two. Drink of water here. If you have any questions along the way, please use the chat or the Q&A. There's also a staff member monitoring that, so if there's technical issues, he'll be helping me with that. I'm just keeping talking here so that those who are joining know whether their audio is working or not. Again, I'll wait another minute or so before I really get going. I said good morning because that's my East Coast Eastern time zone perspective, but good afternoon and good evening wherever you're joining around the world. Sorry that we're not all together in person in Toronto together, but I appreciate the invitation to give this tutorial and glad that we could at least do it in this virtual setting. Again, if you're just joining, if you have questions along the way, I have, as you can see from the slides here, 123 slides, although several of those at the end are bibliography. So there's not that actually many slides to present. So that's long. We'll take a break in the middle, I think. And I think it's much better to have questions along the way than to hold them all at the end, given the length of this and given the large set of different topics that I'll be covering. So again, use the chat and the Q&A, and I've been told we're reaching approaching the number of registrants, so we're going to go ahead and begin. So this tutorial is called Data-Driven Methods for Image Reconstruction MRI, and you'll see some CT examples as well. I didn't want to advertise it that way originally because there's more MRI than CT, but they're both inverse problems. And I've got a picture illustrating the general problem here is to go from undersampled case space data to reconstruct a nice image. Oops, okay. As I mentioned, at the end of the talk, and throughout the talk, there are hundreds of references collected at the end. But if you wanted to sort of narrow it down to 3 key references that you might want to follow up on later, or if you decide you would rather read than listen to me talk, these are the 3 key references. There are 2 survey papers that I was involved in earlier this year, one about the data adaptive and sparse models for image reconstruction, and then one related optimization methods, both of which will be major themes in this talk, and then sort of a current paper from my group from Il-Yong Chun, former postdoc who's now a professor in Hawaii. That's sort of what I consider one of our favorite current methods for deep learning kind of reconstruction of images. And if you want to follow along, the slides themselves are actually on my website right now, and you can download those and do whatever you want with them. All right, so this is going to take you through MRI reconstruction sort of from the beginning, going back to some classical methods, to the state-of-the-art, well, not to the current clinical methods that are actually include compressed sensing-based methods that are based on sparsity, and then moving into, in the sort of the second half more, the research in this field, which is more on the data-adaptive methods and machine learning-based approaches. All right, so let me give you a little bit of history, right? So MRI scans are slow because you collect one point in case space at a time, basically, and so there's been a long history of working on methods to try and accelerate MRI scans to make them more affordable, to make them more comfortable for patients, to reduce motion artifacts and so on. And there's both hardware-based methods for trying to make them faster, as well as different ways of collecting the case space data to reduce how much time you spend collecting that data, and using parallel imaging, which we'll talk about more later, to give us additional information so that we can collect fewer samples. In fact, this has such a long history that even back as far as 1993, people were working on data adaptive methods for choosing which locations in case space to sample. And there's been a very recent trend towards revisiting, or really digging in much more detail, that topic of using training data to choose the sampling patterns. In the last 10 plus years, compressed sensing certainly has been a major theme. Initially, there were conference papers in the 04, 06 kind of time frame, leading to some journal papers shortly after that, and leading to review papers right after that. And then finally, in 2017, the FDA approved compressed sensing methods for MRI, and it's now all of the major manufacturers have FDA approved compressed sensing methods that are used to various degrees by the different manufacturer systems for clinical scans. So this is a real success story, I think, for the imaging science community, the applied math community, that those contributions in sparsity, compressed sensing have led to, you know, routine clinical use of that technology under various names like compressed sense and hypersense in the field. Again, you know, the real focus on this began, like I said, 10, 13, 14 years ago. But again, every good idea has its earlier precursors, and Joram Breslin's group at Illinois was solving sparsity-related problems even as far back as 1998. Those references are all at the end of the talk. So this is already a long presentation, but there's too much to cover even in the amount of time that I have, so I want to give you a sense of the scope of what I'll be emphasizing. I'm going to focus on static imaging as opposed to dynamic imaging. There's a whole other set of tools that are needed for dynamic imaging, and there's some nice survey papers on that in I think the January 2020 issue of IEEE Signal Processing Magazine, if you're interested in that broader scope. I'm going to focus on multiple coil or parallel MRI data as opposed to single coil, because that's what all the vendors use today. And I would argue that any submitted papers that consider single coil MRI are not very interesting. Anybody who's going to do advanced reconstruction methods is going to be doing it with multi-coil data. So that will be my focus. For those of you who are MRI experts, I'm going to be focusing on sense methods that model the coil sensitivities. There are another family of methods that are sometimes called GRAPPA methods that model them in case space, and I won't be giving them as much focus. There's also a whole family of calibration methods that I don't have time to cover. I will be focusing mainly on clinical kind of anatomical imaging as opposed to, say, quantitative imaging, which is a whole other topic of its own. And you'll see there's a considerable emphasis on non-smooth cost functions once we get into the talk. If you're interested in reproducing some of the results in this presentation, I've actually got Jupyter Netbooks linked here on my website in the Julia programming language. That allows you to either play with the code or even just run it without downloading anything using this facility called Binder. I've just as an aside here, I am a real big fan of Julia. I think it adopts the best of MATLAB and Python. You feel when you're using it like it's an interactive language like MATLAB or Python, but it's under the hood, it's a compiled language. So you get performance benefits like you have with C, and it's open source and so on, so nothing to pay for. I particularly like the way the package manager allows you to have very reproducible research. So these binders that I've created here are pinned to specific versions of the toolbox. So even though I continue to upgrade the toolbox, those demos should continue to run because they will use the Git version corresponding to what I was using at the time I created those demos. So that's really great for reproducible research. And if you want to learn more about Julia, I gave a tutorial about it at an IMA workshop on computational imaging last fall, which seems like ages ago now. And so yeah, specifically for computational imaging, I discussed why I like it there. So that's a little plug for Julia there. Okay, some more links to the demos and so on there if you're interested in looking into that. Okay, so let's get into MRI a little bit now. So in MRI, we as engineers have enormous control over the inputs to the system. We design RF pulses and gradient waveforms that are played, if you will, into the patient who has their own tissue properties, and then the magnetization of the object evolves according to an ordinary differential equation called the Bloch equation that's nonlinear. That leads to induced state of transverse magnetization in the object, and then we sense that transverse magnetization using the gradient waveform properties, an encoding matrix that sometimes will be A and sometimes F in this talk. And that's a linear model between the transverse magnetization and the recorded signal. And so I will be focusing mainly on this part of the model here, going from the recorded signals back to an image of the transverse magnetization. Quantitative MRI deals with the topic of going from that further back to quantifying the tissue properties. And like I said, that's a whole nother talk. All right, so we'll have samples basically in a simplified model of the Fourier transform of the transverse magnetization. And our goal is to reconstruct that unknown transverse magnetization from those samples. All right, so this is the notation I will be using. And I'd say probably more than 90% of clinical MRI scans fully sample the 2D Fourier space on a Cartesian grid. So your model is basically that the recorded samples are an FFT of the discretized version of the transverse magnetization. So you simply apply an inverse FFT to the recorded samples, and that gives you the image. And that's what's used primarily in clinical MRI even today. So that would be the end of the talk if that's all we did, because that would be the reconstruction algorithm right there, one called IFFT. But instead, we're going to focus on the more interesting problems, and it becomes interesting in 3 or 4 different situations. One is when you have non-Cartesian sampling. Another is when you collect fewer samples than the other number of unknowns in the object. So you have an underdetermined problem. That's the compressed sensing framework. Or, and I could describe this as a simplified model. In reality, in some kinds of scans, you have to deal with other effects that don't fit into the Fourier framework, such as magnetic field inhomogeneity. Or in combination with the others, if you have multiple receive coils, because this formula here is for a single receive coil. So let's move on to the case where we have multiple receive coils, and now let's actually acknowledge the fact there's also noise in the data. So let's assume we have L receive coils. So the samples recorded by the Lth coil are an underlying magnetization pattern as seen through the coil sensitivity of the Lth receive coil, and then we have our Fourier encoding, and then plus noise. So this C sub L here is a diagonal matrix that has the coil sensitivity patterns along the diagonal. And a coil that's on the right side of the head is more sensitive to the spins coming from that side of the head than a coil that's on the other side of the head. So if we take the measurements from all L coils and stack them up into a tall vector, then we can write that, using a combination of a Kronecker product here and stacking up the coil sensitivity matrices, and finally end up with, a model of the form y equals ax plus noise. And this may be over or underdetermined depending on how many coils you have and how many samples in K space. I'm assuming you're collecting M samples in K space. And by the way, it's the exact same, no matter how many coils you have, it's the exact same samples in K space for each coil. So that's why there's a Kronecker product here, because each coil sees the same Fourier encoding. All right, and this is still a simplified model. Like I said, there's more, some situations need to consider things like relaxation, field homogeneity, but I'll just focus on this model in this talk. And of course, our goal then in any inverse problem is to recover X from the measurements Y. All right, so I'm going back a little bit, and I'll explain why I'm going back in time once we get to the compressed sensing section here. All right, so if the product of the number of coils times the number of K-space samples per coil is bigger than the number of pixels, then this is an overturned problem, and so you could try to use ordinary least squares. All right, which of course has the standard pseudo-inverse solution, and you plug in the particular form for the Fourier encoding and the coil matrices and so on, and you get this form. We can write this down on paper, but in general, this is not practical to implement because this matrix here would be too large to store and invert. This matrix here would be n by n, where n is the number of pixels, and even in 2D imaging, you might have a 128 by 128 image, so this matrix would be 128 squared by 128 squared. Now, if you fully sample K-space, then this inner matrix here, F transpose F, is just a constant times the identity, and then it does simplify to just being the inverse of a sum of diagonal matrices, which is trivial. And this is called the optimal coil combination approach. You're basically taking the data from each coil, taking the inverse Fourier transform of that, and then doing a kind of a weighted combination of those based on the coil sensitivity patterns. There are some other undersampling patterns where F transpose F has a certain simple block structure that you can solve non-iteratively. That's known as classical sense reconstruction. We're going to be focusing on the case where the sampling pattern is irregular and there's no such simplification. And in fact, in general, for general sampling patterns, including non-Cartesian sampling, that problem is ill-conditioned, and so we have to include some form of regularization. And sort of the simplest form of regularization is a quadratic regularizer. So now we're reconstructing the image by reconstructing a cost function consisting of two terms. One term that measures how closely do we agree with the data, all right, or how much do we not agree with the data. It's kind of a misfit to the data. And then another term that in a Bayesian setting would be a log prior, a negative log prior that encourages images to concur with our prior expectations of what images look like. So if we expect images to be smooth, for example, we could make this matrix T to be a finite difference matrix that looks at the differences between neighboring pixels. And so this would, if we don't put such a regularizer there, then we will just be fitting the data. The data has noise and we get a very noisy images, very irregular. This term can encourage neighboring pixels to be similar and we will avoid having so much noise. All right, so this already is a non-trivial optimization problem. It's quadratic, so I guess in setting the field of optimization, it's not too hard, and conjugate gradient algorithm is well suited, but there is an analytical solution here, but the analytical solution depends on this inverse the Hessian matrix that is impractical to compute in practice. So we use typically conjugate gradient algorithms, sometimes with a circulant preconditioner. Now I realize some of you are sitting there thinking, wow, this is really old school. Why is he talking about this? This is 20 plus years old. The reason I'm mentioning it is that many modern iterative algorithms, including deep learning algorithms, actually have a conjugate gradient step as an inner step of those algorithms. And so I think it's important to have that background before we get into the more advanced methods. Now, many of you, I'm sure, are aware that using a quadratic irregularizer has the effect of blurring edges because it strongly penalizes the difference between neighboring pixels. A parabola, as it rises rapidly, really discourages the difference between neighboring pixels. So often we would replace that quadratic function with a non-quadratic function, often convex and smooth, such as the Huber functions shown in magenta here. And since that Huber function rises less rapidly than a quadratic, it penalizes less the difference between neighboring pixels. And so it better preserves edges in the reconstructed image compared to using a parabola or a squared function there. One of my personal favorites of this is the fair potential. It has a particularly convenient form when you take its derivative. And these kinds of methods also have their roots in Bayesian methods for Markov random fields, where these are the energy, the potential function language even has its roots as related to energy functions in Markov random fields. This is now a non-quadratic cost function, and so you need a different optimization algorithm for it. And there's a variety of algorithms that use. Nonlinear conjugate gradient algorithm is particularly effective. One of my former students developed something called the optimized gradient method that is improvement on the famous Nesterov fast gradient method that has the worst case first order convergence for all convex functions with Lipschitz continuous gradients. And recently a group has come up with a line search generalization of that optimized gradient method. So if you have an arbitrary cost function, like convex cost function, like you might have in machine learning, that's smooth, Lipschitz continuous gradient, this optimized gradient method might be a good way to, good technique to use. It turns out in MRI, the cost function is almost quadratic, even if you use a fair potential with a pretty small value of delta. So think of this as like L1 almost, but with a corner rounded. Maybe I should have made that point back in this picture. If you take this magenta curve here and make delta small enough, it's almost like L1, but it's differentiable because you can round at the bottom of the absolute value function. So here's the first concrete example that is one of the ones you could reproduce yourself using the demo if you want, where I've undersampled k-space in this pattern. So 0, 0, the center of k-space, the DC, the low frequencies are here. And so we're fully sampling the low frequencies and then undersampling these other frequencies with a total of acceleration, I think, of a factor of 4. So I think there's only a fourth of the overall samplers are being recorded here. This is the true Shep-Logan phantom in the simulation. If you just take this data and then do an inverse Fourier transform of it and look at it, you get this image that I hope you can see over Zoom. Has all sorts of ringing artifact and aliasing artifacts in it. The ringing kind of comes from the, if you will, the truncation of K-space here, and the little ripples and so on come from the random sampling outside. So this would not be an acceptable image. But if you take this same data and you put it through the cost function I showed on the previous slide, and minimize it with some algorithms, you can get this edge-preserved reconstruction that you can see has pretty close agreement to the ground truth. And by the way, there's no sparsity here, no explicit sparsity, right? It's just edge-preserving regularization. I compared 3 different algorithms here as a function of iteration, plotting the cost function. And so the blue curve here is Nesterov's famous fast gradient method, or accelerated gradient method it's sometimes called. The orange triangles here are this optimized gradient method that has a worst case convergence bound that is a factor of 2 better than Nesterov's algorithm. And you can see that you reach any given point on this at about in half as many iterations. But for this particular cost function, even though it's non-quadratic, the nonlinear conjugate gradient algorithm converges even faster. And I think the reason for that here is that this cost function is probably locally strongly convex, and OGM and FGM are not optimal for functions that are locally strongly convex, whereas CG is quite effective in that regime. And the final root mean squared here is only 1.5%, so that's quite good despite the factor of 4-fold acceleration K-space. So this has motivated, of course, tons of research on sparsity kinds of models and compressed sensing. And you might still be surprised that I'm going to spend as many slides as I am on compressed sensing, given that it's not an adaptive method. And the reason, again, is that compressed sensing led to quite a few different optimization algorithms. And many of those optimization algorithms have served as the foundation for deep learning-based methods that are, of course, where the current research is. So in fact, there was just recently a paper describing a challenge for MRI reconstruction, where several groups submitted to a leaderboard advanced machine learning-based methods for reconstructing knee images from training data. And all 3 of the winning groups, this is a quote from the paper, chose approaches that used a combination of a learn prior, so that's the machine learning part, and a data fidelity term that encodes information about the MRI physics of the acquisition, in line with approaches that can be seen as neural network extensions of a classical iterative image reconstruction methods. And in fact, if those of you who might have attended Friday's tutorial on advanced reconstruction methods, that was also a prominent theme in that tutorial, that combinations of machine learning and iterative algorithms, unrolled loop kind of algorithms that I'll be talking about as well, are kind of the state of the art, I would say, in image reconstruction. And I think to understand that state of the art, you need to understand the iterative algorithms even for, say, classical compressed sensing now. So I'm going to spend some time on that before we get to the truly adaptive methods. So in this field of sparsity, there's sort of 2 main categories of sparsity models: analysis models and synthesis models. So in a synthesis model, you assume that your unknown image, in this case, can be synthesized as a linear combination of some columns of some matrix using a sparse set of coefficients. And I use the letter B because you kind of think basis, but you don't say basis because usually this matrix is wide, so it's over complete. So it's not, it can't have linearly independent columns. So it, strictly speaking, can't be a basis, but in a sense, it's like a basis. All right, and since you expect in this model, and again, there's this expression that I wrote at the bottom of the page, all models are wrong, but some models are useful. It's very debatable whether any real world images in MRI actually satisfy this model exactly, but if you're going to undersample case-based data, you have to impose some kind of model to make up for the missing data, and the models on this page are 2 of the models that have been used effectively to make up, to sort of reduce the degrees of freedom somehow in the reconstruction problem. So this is one way of sort of reducing the degree of freedom, is assuming that your image can be expressed as linear combinations using sparse coefficients. Sort of the dual of this is an analysis model where you assume you have some matrix T, a transform matrix that you apply to your image, and the result of that matrix vector product is a sparse vector. So in that case, you might use a regularizer that involves something like the 1 norm of the product T times X, because you're assuming that that product is a sparse vector. At the time I first made these slides, I said this was most likely used in the recent FDA-approved compressed sensing methods. I've since had conversations with people in the companies, and I know a little bit more about what's under the hood, and this is indeed the kind of regularizer that's being used as we speak in the compressed sensing methods, at least in some of the companies' compressed sensing products. Now, these two models turn out to be equivalent if the matrices are square and one is in the invertible and one is invertible. One is the inverse of the other. But usually they're not square. Usually the basis, the dictionary we use here is wide, so over complete, and usually the transforms are tall. All right. And I'd say this is still somewhat a debate in the field of which of these models is preferable. Using this model is a little bit easier because your one norm is applied directly to the coefficients and there's no matrix inside of the one norm, so it's a little easier for the computation algorithms. Whereas with the analysis model, you have a matrix inside the one norm that makes it a little bit harder for optimization. But on the other hand, you'll see in a second that the synthesis model usually has more unknowns to manipulate because the number of coefficients here is usually bigger than n. And so there's a potential trade-off there. So let's dig into that a little bit more. So if you believe in the synthesis model, if you believe your image can be represented as a linear combination of some columns of a dictionary, then this is a logical way to set up the optimization problem. Find the set of coefficients that when I synthesize an image from those coefficients and then propagate that to k-space, I get agreement with the data, but at the same time, I want those coefficients to be sparse. All right, so this is a convex optimization problem. It's convex because we use the one norm instead of a zero norm here to count the number of non-zero coefficients. And this is a famous problem in statistics called the Lasso problem, and there's lots and lots of optimization algorithms for it. Many of you have probably used, if you've worked on a problem like this, you've probably used ISTA, the iterative soft thresholding algorithm, or you might have used FISTA, the fast iterative soft thresholding algorithm. I'd like to encourage you to look at an algorithm called the proximal optimized gradient method. That is an improvement on FISTA, and I'm going to show results on that in just a minute here. So let's first review those classical ones. That the iterative soft thresholding algorithm, also known as the proximal gradient method, basically takes a descent in the gradient direction. So this right here is the gradient of that cost of this data fit term in the cost function I just showed you, and then it applies soft thresholding to that gradient update. And because soft thresholding is the proximal operator associated with the one norm. All right, so it's a very simple algorithm. It's like one line of code in Julia or MATLAB once you set this stuff up correctly. The classical version, you'd have a step size here. I actually tend to use a different version that has a diagonal matrix here that satisfies a certain majorization condition. And the reason I do that is that the classical approach requires finding a Lipschitz constant, which is a spectral norm that is often inconvenient to compute. These matrices are really large, and so computing a spectral norm can be quite expensive. Whereas I have references here on tools for finding an easy to invert, diagonal matrix that satisfies this inequality, meaning D minus this product is a positive semi-definite matrix. And that doesn't require computing any spectral norms. So that's the version that I tend to use. Unfortunately, this algorithm, as simple as it is, has an order 1 over k, where k is the number of iterations convergence rate, which is annoyingly slow. And that's why people tend to use FISTA instead, because it has an order 1 over k squared bound, which is a huge improvement. This is also known as the fast proximal gradient method. Now, I want to generalize this a little bit. The cost function I showed a couple slides ago here, this is a sum of a smooth term plus a non-smooth term. All right, and such cost functions are called composite cost functions. When you have a sum of a smooth term, typically a data fit term, and then some non-smooth term, typically a regularizer, often involving sparsity or constraints. And typically when people focus on composite cost functions, they're considering non-smooth terms that are what are called prox-friendly. It's easy to compute the proximal operator for those. And my favorite algorithm these days for this kind of cost function is called the proximal optimized gradient method, because it has a worst case convergence bound that's about 2 times better than FISTA. And in practice, my observed case performance is similar to that factor of 2 improvement that the worst case theory tells you. And I'm going to show you the code in a second. It's extremely simple to implement. If you've implemented Vista, it's like a one-line change to make it FPGM. Same amount of time per iteration. Most of the time is involved computing the gradient of the smooth term. And then depends on how prox friendly your proximal term is. But I want to point out, even though that's my current favorite, this is an active research area, and there's people continuing to push on making faster algorithms for this particular family of cost functions. So this is what the proximal optimized gradient method looks like. So the parts shown in red here are what you have with Vista. So Vista involves a gradient step involving the gradient of the data fit term. And then there's these magic momentum factors that Nesterov somehow came up with that are kind of mysterious. And then you combine those momentum factors with a certain update that involves the difference between these intermediate variables at the previous two iterations. That's the momentum. And then finally, and then at some point in Vista, there's also a proximal step, which in general, I've been saying proximal operator multiple times and I haven't defined it. Here's the definition of a proximal operator. It's the minimizer of a quadratic term plus whatever the function is you're applying the prox to. So if this was the one norm here, that would be the solution to this is soft thresholding. So the proximal optimized gradient method is an extension of Vista, if you want, that has these additional terms that are shown in blue. So there's a slightly different magic momentum factor for the very last iteration, for the nth iteration. And along the way, there's a couple extra momentum-like terms that involve differences between various quantities. Adrian Taylor, who came up with this method, I think uses what's called computer-assisted proof to find this. You can read his paper to learn more about that. He has nice software tools for helping develop algorithms in that way. So you can see it's a very small change to the code. It does require maybe storing 1 or 2 extra copies of variables, but that's not a big deal memory-wise. And you can further speed this up using something called adaptive restart. So if your momentum starts to point in a direction that is too different than your gradient, then you often reset and go back and refer to the gradient and sort of reset, if you will, to the iteration counter back to 1 and thereby sort of dampen the momentum. This is especially useful if your cost function is locally strongly convex. All right, so here's a concrete example. Same data that I showed you before, but now a different cost function. I'm using my B here as an orthogonal discrete wavelet transform. All right, and so I have a 1 norm on the wavelet coefficients here. And then I'm plotting the cost function versus iteration here. And the blue curve is the classic iterative soft thresholding algorithm, proximal gradient method. The orange is the order 1 over k squared convergence rate that you get with Vista. And then POGM also has an order 1 over k squared worst case convergence rate, but with a better constant. And you can see that better constant leads to, additional acceleration. It's not a gigantic additional acceleration, but given that it hardly takes any more work to implement, in my experience, it's worth it, and we've used it for quite a few different applications. All right. Okay, so there's a question here. Okay, the question is there a version of this for more than 2 functions? So that's an excellent question. So first of all, if you have more than 2 smooth functions, you would just add them together and that would still be smooth. I bet that's not what you meant. I bet you're wondering if your prox term has more than 1 non-smooth function. So you might have, for example, a 1 norm and maybe a constraint. In CT, you might have a non-negativity constraint. Now that particular combination I just mentioned there, a 1 norm and that still can be combined into a single non-smooth term that is prox friendly. But if you had something like you wanted total variation plus a non-negativity constraint, well, TV by itself is already not prox friendly. And then if you add other things to it, it's even less friendly, I think. And so I think my answer to your question is I don't know of any general case way to handle more than 2 prox friendly terms. There is a field, I'll just mention a term, there's a method called proximal averaging, where if you have multiple non-smooth terms, each update uses just one of those terms. and you sort of cycle through the different terms, or you apply them individually and then you take the average. And the average of a set of proximal functions, proximal operators, is in general not the same as the proximal operator of the sum of those functions, but people have made inroads into some convergence theory, even though you're sort of applying those non-smooth terms one at a time. So let me leave it at that as my initial answer, and if you have more questions about that later, we could follow up on that later. And so actually that's a great lead into, so everything I just described was focusing on synthesis-based sparsity. Oh, and I should have mentioned, by the way, I'm sorry, I forgot to say one thing about this. A drawback in my view of the synthesis form is that your final image is going to be in the span of your matrix B. So you have to really believe that you have a reasonable basis, over complete dictionary, that a linear combination of those columns can represent the image that you want. This is not an approximation, this is an equality. This is saying, I'm gonna finally synthesize my image using my basis, using my dictionary. And that's an open question whether we really know the right models to use in imaging. So that's a drawback, I think, of that potential drawback of that formulation. In an analysis model, you don't have that kind of same hard constraint. You put an analysis regularizer in, you still have your data fit term as it is. So you're finding an image that trades off fit to the data, and in this case, sparsity of some transform of the image. But you never require that your image lie in the span of any particular operator. So I feel like this might be a little bit more robust to having an imperfect choice of the operator here. And all choices are imperfect. Yeah? The most common choices for this matrix T are the wavelet transform, some wavelet transform, finite differences, and if we use finite differences, that's related to total variation, or in the original sparse MRI paper by Mickey Lustig et al., they used a combination of both of those operators, which you could think of as sort of just stacking up different matrices here, making this matrix T even taller. And I'm quite sure that the FDA-approved methods that are out there are basically, at least for some of the manufacturers, are related to this cost function. Unfortunately, this cost function is harder to optimize because of the matrix T inside of the one norm. All right, so what are your choices here? You could try applying ISTA or the proximal gradient method. You'd take a gradient step, and then you'd have your proximal operator step, but unfortunately that proximal operator step requires minimizing a cost function. It's a little easier than the original one because there's no matrix in front of X in the 2 norm, but we still have a matrix X in front of the 1 norm, and there's no closed form solution to that in general, unless T happens to be unitary. So then you need iterative methods to solve this inner proximal problem, and this is, now you have iterations within iterations, and I'm not a huge fan, if I can avoid it, of having those sort of nested iterations. As I mentioned, this is the classical version where you put the Lipschitz constant here, and how easy that is to compute depends on your application. In single coil MRI, this is easy. In multiple coil MRI, it's a little bit harder, especially not in Cartesian parallel MRI. All right, so the POGM, these kind of first order methods are not as attractive for the analysis formulation because of that matrix T. So what can you do? Well, one operation is you can punt and say, well, let me just replace my 1 norm with an approximate 1 norm by rounding the corner of the absolute value function. Lots of papers have done that. And once you do that, you're basically back to edge preserving regularization, and you might as well use nonlinear conjugate gradient for it because that works quite effectively. But then you don't get any pure sparsity. You'll get some shrinkage of some of the coefficients, but you won't get any zeros once you round the corner. You need that non-differentiability. There's nice work by Mila Nikolova to show that. An alternative approach is you replace this, this regularizer right here with an alternative, a penalty approach that says, well, I want an image whose transform is close to a vector Z where I want that vector Z to be sparse. And there's quite a few papers that use this kind of formulation. So we want an image that fits the data, but we also want to fit an image whose transform is close to some sparse coefficients. Now it turns out if you do this, you can actually, for the 1 norm here, solve this problem analytically, and it turns out that this just becomes the same as using a Huber function, so we're back to just a different form of corner rounding. And then there's a iteratively reweighted least squares method that I won't talk about more here. All right, so if you really feel like you want the exact one norm, then probably your best bet is to use an augmented Lagrangian or ADMM kind of method, where you replace the original cost function with a constrained version. So you introduce an auxiliary variable z that you define equal to tx, so then you put that variable z inside the one norm, and now we have a constrained optimization problem in two variables. We're minimizing over x and z subject to an equality constraint. And at least now we've gotten rid of, there's no matrix inside the one norm, all right? And there's a whole bunch of related algorithms, split Bregman, augmented Lagrangian, ADMM, and Dudley-Rashford, that are kind of all variations of methods for, or often equivalent methods for solving this constrained optimization problem. And if you write down the augmented Lagrangian for this problem, it has your data fit term, it has that one norm for the sparse coefficients, it has a term involving Lagrange multipliers, and then this is the augmented part of the augmented Lagrangian, where there's a quadratic term that involves the difference between tx and z that came from the initial constraint that we want in the limit tx equals z. This parameter mu here is called a AL penalty parameter. This affects the convergence rate, but not the final solution x hat. It turns out it's convenient to make a little change of variable and get something called the scaled augmented Lagrangian, which now has these 4 terms in it. So there's really 2 primal variables here, x and z, and then a dual variable eta. And we alternate between doing descent in ADMM. You alternate between doing descent updates of the x variable, the z variable, and then an ascent update of the scale dual variable eta. So let's actually walk through that, because again, these versions of this kind of algorithm have appeared even in the modern deep learning kind of methods. So I've color-coded here things, color-coded the variables here. So we have the augmented Lagrangian here. There's no closed form solution to this, so we need to apply iterative methods, and we're going to alternate between these different variables. So when we update z, you notice z just appears in these 2 terms here, and this is simply the proximal operator, basically, of the one norm applied to the quantity tx plus eta, so we apply soft thresholding. Simple update for z. If you look at where x appears, it appears in a quadratic term here and another quadratic term here, so that's perfect for using the conjugate gradient algorithm. So this is an example of where knowing about CG for quadratic is really valuable. I've written it here in the closed form solution involving the matrix inverse, but in practice, unless it's single coil Cartesian MRI, you will probably need to iterate to update x. And then finally, the update for eta is in an ascent direction. And there are variations of this for how you choose mu and other variations of this algorithm. So you've taken a hard optimization problem and sort of manipulated it to get a sequence of 3 different easy updates that you cycle through. It turns out for parallel MRI, there's a little bit more involved but advantageous version of this, where we exploit what I just showed you on the previous slide would apply to lots and lots of applications, not just MRI. If in the application MRI, we have some particular structure to our problem. Our problem involves an undersampled FFT and coil sensitivity matrices. And the undersampled FFT has the property of being related to a Fourier transform, and F transpose F has certain properties. The coil matrices are diagonal, that's a certain property. So it turns out it's beneficial to introduce more auxiliary variables. We'll let U equals CX here, we still have the sparsity term, Z equals TV. We introduce Z just as an extra variable with a constraint V equals X. All right, and I don't think I'm going through all of the details here, but just letting you know that once you make all of these variables, and then write down the augmented Lagrangian, which is much longer now because we have 1, 2, 3 constraints plus these 2 terms, so there'll be a total of at least 5 terms involved there. Each of the updates becomes really simple. You don't need any conjugate gradient. When you do the X update, turns out you only need to invert a diagonal matrix. The V update involves T transpose T that is often circulant or toplets, so very easy to invert. The U update involves F transpose F that is circulant in the Cartesian case and toplets in the non-Cartesian case, so you can really effectively either just invert it with FFTs or do a couple iterations of a circulant preconditioned CG. But now there's more parameters to tune. That's the only drawback. So there's, anyway, if there's references here if you want to look into that in more detail. There's also a family of duality methods for dealing with this matrix inside the one norm, and I'm not going to give the full story here. I'll just say the essence of the idea is that you can rewrite this one norm as the maximum over a set of dual variables whose maximum values at most 1 of the inner product of those dual variables with t times x. So you've replaced, in essence, the one norm with an infinity norm. An infinity norm is like a box constraint, and that's kind of easier to deal with in many optimization algorithms. And so you can rewrite the original analysis regularized problem as a minimization over 2 variables, one unconstrained and one having these box constraints, with now an inner product here. And you can sort of do alternating updates between x and z. I'm oversimplifying, but that's the essence of the idea. So there's a family of methods called Shambo-Pock methods or primal dual methods relating to solving it in this form. All right. This is a good point to pause. Okay, somebody's asked the question, is x in Rn or Cn? So in MRI, x is always in Cn. In the image reconstruction problem in MRI, the transverse magnetization is a vector that has a I and j component, and we represent that vector using complex numbers in MRI. And in fact, I mean, it's not just a mathematical representation. The scanner itself, the receive coils go through I and Q channels, so there really are 2 A to D converters collecting an in-phase and quadrature component. So there really are, I mean, there's 2 streams of numbers, and it's most natural to associate those 2 streams of numbers as the real and imaginary part of complex numbers. And the whole Fourier way we're writing it down is assuming that. Now, once you've reconstructed the images, for display to a doctor, you typically just take the magnitude, and a whole lot of image processing is typically just done on the magnitude of the reconstructed images. So those are then real images. But the reconstruction problem is done with complex images. So I hope that answers that question. I'm gonna get a pause for a sip of water here. All right, well, I am zooming along here. So now we'll get into more advanced forms of sparsity, but still not yet adaptive, but this is transitioning towards the adaptive version. Oh, I think I'll skip this slide. I just want to acknowledge, I've been focusing on the sense framework, and there's a whole family of methods that are based on case-based models instead of image-based models called graph methods, and I'll give you those references if you want to look into them. And there's also calibration methods. Now I'm going to get into the more advanced sparsity models. Sorry. All right. So if we use a total variation or an edge-preserving regularizer that looks at the difference between neighboring pixels, we're essentially taking patches out of an image of size 2 by 1 or 1 by 2. This is very, very local information, right? We're assuming that the neighboring pixels tend to have similar values, or their differences tend to be sparse. You could say that's very myopic information, very, very, very narrow sense, right? It kind of stands to reason that you could better model images if we extract patches of bigger sizes than 1 by 2 or 2 by 1, you know, patches of size 3 by 3 or 8 by 8. And in fact, you know, CNN methods these days mostly use 3 by 3 filters, but use a cascade of several filters. So the receptive field is typically quite a bit bigger than even 3 by 3. So let's talk for a little bit. And of course, JPEG image compression uses 8 by 8 patches and so on. So there's a long history in image processing of using patches that are much bigger than 1 by 2. So in the patch framework, there are 2 families of methods, synthesis models and analysis methods as well. I want to talk about both of those. So let's start with a patch-wise dictionary sparsity model. So in this model, instead of trying to model the entire image using some dictionary, we extract patches from the image. So here's a whatever it is, 10 by 10 patch extracted from an image, and we're going to assume, so that's this matrix piece of P means the pth patch extracted from this image. So that matrix is a very wide matrix that is mostly zeros and a few ones that just picks out the pixels in this patch from this, in this case, actually 3D volume. And we're assuming that that patch can be well represented, approximately at least, by a sparse linear combinations of a typically over-complete dictionary. This dictionary now only needs to model patches, not the entire image. Much more, I think, feasible and reasonable approach. All right, so that's the concept. Let's turn that into a mathematical regularizer, right? So again, I mentioned we have this patch extraction matrix. Let's assume somehow we've come up with a dictionary for what we think is good for sparsely representing these patches. All right, so a natural approach to image reconstruction that uses this model, this idea right here that the patches can be approximately represented as sparse combinations of atoms from a dictionary, is to minimize a cost function. That's, as usual, two terms, a data term, and then a regularizer where the regularizer says, I expect each patch to be close to a linear combination of atoms from a dictionary where I expect the coefficients in that linear combination to be sparse. So I'm going to be minimizing over the set of possible coefficients. So plausible patches are those where this term is small, that there exists some sparse set of coefficients that can represent it. And this parameter alpha is pretty important. If you let alpha go to 0, then you're not putting any sparsity at all, and every patch can probably be represented perfectly by some linear combination of the dictionary, atoms in the dictionary, and basically your regularizer is 0 then. So this is only useful if you set alpha large enough to really encourage some sparsity in this representation in hopes of therefore sort of denoising the patch, right? Noisy patches cannot as well be represented by a sparse linear combination of atoms in the dictionary as good patches that are less noisy. That's the idea here. So this is a little bit harder optimization problem than what we started with earlier, because now we have two variables to minimize over, the image X and the sparse coefficients. But if you look at this, when it's very natural to apply an alternating minimization algorithm where we alternate between updating the image X and then the sparse coefficient Z. We sort of move this min over Z outside, so double minimization. When we're minimizing over X, you notice there's a quadratic term here, quadratic term here. Once again, conjugate gradient's the natural thing to apply there. When we're minimizing over Z, fortunately, there's no matrix in front of Z here, so this is simply, oh no, but there is a matrix in front of Z here. So this is a sparse coding problem. And so actually I recommend using the proximal optimized gradient method for that inner problem in minimizing over Z. You could also think of it as lasso and apply any of your favorite lasso algorithms. But my favorite lasso algorithm is proximal optimized gradient method. I think I'll skip that detail. Any questions? No. So that's the synthesis approach to patch-based regularization. The analysis approach extracts patches from candidate images and assumes that there's some transform that when we apply it to those patches, we assume that transform is sparse. So this transform could be either learned from data, like we'll talk about in a minute, or it could be a hand-specified transform, such as a discrete cosine transform, like used in JPEG image compression. So if you believe in this model, if you believe a transform of your patches is sparse, then a natural regularization approach is this cost function, where again, we want to fit to the data, and then we want to find images that when we extract patches from them, the transform of that patch closely agrees with some coefficients that are sparse as quantified by the one norm. So again, alternating minimization, the way to go here. X update is quadratic. The Z update is simpler now, because now we have a one norm here and we have a two norm with no matrix in front of the Z. So this is just soft thresholding, which is much easier than running an iterative sparse coding algorithm. So this is one of the reasons I personally kind of prefer the analysis approach over the synthesis approach, because this optimization problem is much simpler. Just as a side comment, in case you're thinking about implementing this, if you did it in a naive way, sort of following the two bullets here, you would find yourself storing an enormous number of coefficients. And when you get to 3D imaging, you'll find that uses up a lot of memory. The way you do this efficiently is you don't compute all the Z's at once. You compute one or a few of them at a time, and then you plug them back in and you do some accumulation, and you get kind of a running image through accumulation, and so you only need to store basically one extra image plus, you know, one or two sets of coefficients at a time. We'll come back to this expression again later in the talk. This turns out to be important for deep learning methods. question about how big are you thinking of the patches? That is $1 million question. And so I think it depends on how much training data you have and how much memory you're, time. And let me get to that in a minute. Okay, it's a great question. For some reason, people in signal processing often use powers of 2, like 8x8 and 16x16, because probably historical reasons having to do with the JPEG image compression. And it probably used 8x8 because the DCT is related to the FFT, and powers of 2 are convenient for the FFT. I'm not sure those powers of 2 make any sense today for the kinds of operations we're doing here that don't have any FFTs associated with them once we get into learned transforms. So it's a great question. And I don't have a good answer for that. It's an empirical thing, I think. But let's just say, be thinking on the order of 8x8 or 8 cubed in 3D. Yeah, okay, so just a preview of where we're going to be going with the neural network methods. Again, the same cost function here. I mentioned that when we do the Z update, we can put all the Z updates together to form this intermediate image. So we've got our current image, we apply the Z updates, and that turns out to involve some soft thresholding. So you're basically taking patches out of your current image, taking their transform, applying a soft threshold to that transform, undoing your transform, and then basically putting those patches back together in an image. And the result of that is essentially a denoised image if your transform is any good and if your thresholds are chosen appropriately. So you've taken your current image, you've denoised it, and it turns out once you rewrite this after solving this, this regularizer then turns into just the simple Tikhonov-like, shifted Tikhonov-like regularizer that involves the difference between X and that synthesized or denoised image. And so this is, now we get to use the case-based data again, the physics of our imaging system. And this algorithm is basically alternating back and forth between using the physics and doing some kind of denoising. And once you understand that, it's natural to say, well, let me throw this away and replace it with some other denoiser, non-local means, block matching 3D, or a CNN. And we'll be getting there a little bit later. It definitely kind of, in my mind, directly came out of alternating minimization applied to this cost function. All right, now let's see, let's get into the, now we're starting, getting closer to the adaptive models. Actually, I have one more non-adaptive regularizer here, convolutional regularizers. Okay, so this is closely related to the patch models, and there's both synthesis and analysis versions. So this is sometimes called convolutional dictionary learning, goes by a number of different names, but in this model, we're assuming the image can be expressed as a sum of some filters convolved with arrays that are sparse. So you can think of them as sparse coefficient images. So think of them as like the Z's, think of them as like the night sky, mostly 0 with some small number of non-zero values in it, and you convolve that with some filters and then add those up and you synthesize your image in that way. You can think of these H's as sort of patterns, and we're synthesizing our image from placing those patterns in different places. And if we have enough patterns, we add them all up, we can hopefully do a good job of synthesizing our image. This is challenging from a storage point of view, by the way. We might need a lot of these sparse coefficient images. But let's just go with it for a moment. So if you believe in that model, then again, the natural regularizer here is one that says I take my candidate image and I see how well does it agree with being expressible as a linear combination of filtered versions of some sparse images where we measure the sparsity with the 1 norm here. So again, alternating minimization between a quadratic update for X using conjugate gradient. And then for Z, this is again a sparse coding problem. This convolution is equivalent to a matrix here. So we have a 1 norm and we have a matrix here. And again, I'd recommend POGM for that Z update. That's the synthesis model. And it's a little bit hard because of this sparse coding step. So let me instead focus more on the analysis model here. Again, with a convolutional model. So in this model, we believe that if we have plausible images and we apply certain filters to those images, we expect the outputs of those filters to be sparse in this model, where we have to choose appropriate filters. And in fact, when we do that with finite differences for total variation, where our filters are just 1 and -1, for example, that's essentially what we're doing. We're using essentially a convolutional model there. So more sparse images, more plausible images are those of sort of higher likelihood and are higher prior in a Bayesian setting, or those for where these outputs are more sparse. There's no patches in this, right? It's inherently shift invariant. So here's an example of a handcrafted image and some handcrafted filters. So if I take this particular image and convolve it with these 4 filters, I get these 4 outputs, and all 4 of them you can see are reasonably sparse. This one's especially sparse, but even these others are pretty sparse. The gray is 0 here, and the white and black, or the brighter and darker, are the non-zero values. So for an image like this, I can probably handcraft appropriate filters that would lead to sparse outputs and then use that as a regularizer. But it's probably not very useful image in MRI. Now, if you think that's a good model, then your regularizer, again, was going to take the difference between convolving the image with those filters and comparing to coefficients that we want to be sparse. And you've got the theme now. We've got alternating minimization with a quadratic update for x. And here the z update is extremely simple. Nothing in front of z, so it's just soft thresholding. And if we do those z's updates one at a time and accumulate them, we end up again with something very similar to what I showed you on a previous slide, where we take the current image, we filter it, apply soft thresholding, convolve it with the transpose of the filter, or the reversed of the filters. What in CNN sometimes people call deconvolution, which I think is a horrible term. Well, this is being recorded and I'm saying that. Well, anyway, it's adjoint convolution is the right term, but anyway, and you sum those all up. So that actually ameliorates the storage problem. You're only sort of storing one set of these filter coefficients at a time and then accumulate them. And then finally you do an X update that involves the imaging physics and this denoised image. So again, now this is starting to look a lot like a CNN that has a bunch of filters, ReLUs or some other soft thresholding function, and then more filters. All right, so to summarize, we talked about both sparsity from a synthesis and analysis point of view, and then we did the same thing with patches, and the same thing with convolutional models. And you see the recurring theme in the algorithms here was alternating minimization using conjugate gradient for the smooth part of it, the quadratic part, and then some kind of proximal operations like soft thresholding for the non-smooth part, and using duality methods if we need to for some of the more complicated regularizers. All right, I'm going to pause again here if there's a breaking point. Any questions? All right, so we have now finally reached the data-driven part. All right, so how far are we in here? 1 hour in, okay. Sorry to keep you in suspense that long, but I hope this is useful. I know it'll be useful for my future students when they're starting to work in my group. All right, so everything I've discussed so far, the filters, the transforms, the bases, whatever, were all chosen by mathematical ideas like DCT or finite differences or whatever. And of course, these days we have lots of data available. It makes sense to try to learn those components from training data of some sort, right? So instead of handcrafting these terms, let's try to learn them from data. I can't resist making my usual joke. If you're making wine or cheese, then handcrafting is a good thing, right? It's artisan to have artisan handcrafted cheese. But apparently, if you're making a regularizer now, handcrafting is a bad thing, and we should instead be letting the data speak for itself. Now, even in that sense of adaptive, letting the data speak, there's at least 2 different ways of doing it. And I'm going to emphasize that difference here. There's one approach that I'll call population adaptive, where we have a whole bunch of hopefully good quality training data, a population of training data that we hope is representative of future patients, and we try to learn a dictionary or a transform or filters from that training data that we use in later reconstructions. There's another form of adaptation that's less perhaps well known, which is sort of patient-specific adaptation. It's sometimes called blind adaptive methods, where we actually have a model that involves a dictionary, but instead of pre-specifying that dictionary or instead of learning that dictionary from population, we actually learn it from this patient's data as we're reconstructing that data. And you can do that whether you're trying to learn dictionaries or transforms or perhaps even filters. And even recently, there's been some hybrids that try to take a combination of both, where you try to learn sort of part of the transformer dictionary from a population, but you recognize that your current patient might not be exactly representative of that population. So you refine the model in some way based on this patient's own data. All right, so hopefully this is getting to be a little bit newer for many of you, and I will talk some more in detail here. Now, yeah, you'll see this as a theme. Once we start adapting in this way, you have to put some constraints on learned components. And I just want to, for those of you who don't know, this theme of using machine learning-based ideas, and we're very much getting into the machine learning frameworks now, is hot enough or whatever that there was, well, I guess now 2 years ago was a whole issue of TMI devoted to this topic. Now here I'm borrowing a slide from Daniel Kremer's and Michael Muller's nice tutorial on Friday. We also, now everything I've shown you up until this point was convex cost functions, and almost everything I think I show you hereafter is going to be non-convex. And so the optimization problems are harder, but they made a very interesting point that you probably need non-convex regularizers to really get good image quality. So let me just summarize. They point out here that if you have a convex regularizer and you take a convex combination of two images, then that image that's the convex combination will have a lower value of the regularizer than at least one of the two images you started with. And visually, that makes no sense at all. This image to us, obviously, is clearly less plausible as a natural image than either of these two images. And so I thought they made a pretty compelling case why we probably need non-convex regularizers in order to get the maximum information out of data. All right. So I will be entering into the non-convex world in probably the remainder of this talk. All right, so to do adaptive-based regularization, you have a number of choices. I already mentioned you can treat the data either in a population adaptive way or a patient adaptive way. Oh, and I should mention, by the way, one of the reasons you might do patient adaptive is in situations where you don't have enough training data. For example, dynamic MRI, it's virtually impossible to get fully sampled data at the spatial and temporal resolutions that we really like to train from a population. Although people are working on self-supervised methods to get around that, but let me just leave it at that for the moment. So there's a choice you have to make. You have to make a choice in terms of how you're going to form the regularizers. It's going to be patch-based, convolutional, or something else. And then as you've seen, you have to choose between synthesis and analysis. So there's at least 3 categories with 2 choices each. So there's at least 2 to the cubed options here. And I'm going to just show you samples, I think 2 out of those 8 possibilities. I'm going to start out with a population adaptive method with a learned transform. All right, so population in terms of the data, a patch-based model in terms of structure, and then analysis formulation. So we'll be learning and using a sparsifying transform. It so happens I'm going to use CT for this example. So again, to remind you of this model, in the transform sparsity model, we believe that there exists some transform that if we extract patches from the image and apply the transform to those patches, we should get sparse coefficients. So the question is, what transform should that be? And in a population adaptive setting, let's try to learn that transform from training data. All right, so let's assume we're given good quality images. In CT, these would be well-sampled or high-dose CT images that are out there in a database. We extract patches from that training data, and then we try to learn a transform that when we apply it to those patches, we get transform coefficients that are sparse. And so now, if you didn't put any constraint on the learned transform, you would end up with just learning 0. Because obviously 0, the transform that's just a matrix of zeros, would make the coefficients very sparse. So we have to constrain the transform in some way to make this a non-trivial optimization problem. And the simplest, perhaps, constraint is to make the transform unitary. People are working on generalizations, but I think that's the simplest place to start. So we want to learn a unitary transform. So again, just to make this concrete, let's suppose your patches are 8 by 8. Then this transform matrix would be 8 squared by 8 squared matrix that we want to be unitary. And here you'll notice I've used a 0 norm instead of 1 norm. I told you I was going to enter the non-convex world. And the reason is the set of matrices that are unitary is a non-convex set. So just writing that down, we've already made this a non-convex optimization problem. So we might as well just embrace non-convexity in its fullest and count the number of non-zero coefficients instead of putting a 1 norm there. So those are 2 sources of non-convexity in this problem. I want to make a little contrast between this approach, by the way, and the KSVD approach, which is a popular approach to dictionary learning. In this cost function, I am counting the total number of non-zero coefficients in the transform of all the patches. I don't care if some patches have 1 or 2 non-zero coefficients and others have 10 or 11 non-zero coefficients, as long as the sum of the number of non-zero coefficients over the entire image, actually over the entire set of training data, is small. If you think about medical images or even natural images, there's regions in the air and uniform regions where the output is especially sparse, and then there's other regions that are much more complex. In the original KSVD formulation, they had a certain constraint, you know, K, that's what the K is, on the number of non-zero coefficients for each patch. And I don't think it makes sense to use the same constraint for every patch. I think it's the total number of patches, the total number of non-zero coefficients, the aggregate non-sparsity that really matters. And so that's what we've written down in this formulation. But you of course could do it differently. You could have a indicator function here that is constraining the number of non-zero coefficients for each patch individually if you prefer to do it that way. All right, so we have a double minimization problem, minimizing over both the transform and the coefficients from training images. And you bet, you can guess that we're going to do alternating minimization here. So when we minimize over the coefficients, there's no matrix in front of Z here, there's a 0 norm here, so this is just the proximal operator for the 0 norm, which is hard thresholding. So you take your current guess of the transform, you apply that to all of your patches, and you do hard thresholding of it. Then when it comes time to update the unitary matrix T, this turns out to be what's called the orthogonal Procrustes problem. You've got a vector here, a collection of vectors, you group them together, and you can solve that problem using a simple singular value decomposition. And it's not a big SVD, it's an SVD of the size of your transform. So if our transform here is 64 by 64, then you're going to only need to do an eigen decomposition of a 64 by 64 matrix. So completely practical. Despite the non-convexity, there is work showing some convergence guarantees for this alternating minimization. Not guaranteeing convergence to a global minimizer, but at least convergence to some kind of local minimization property. You don't get stuck partway down at a saddle point or whatever, I believe is the nature of those guarantees. All right, so let me show you a concrete example. This is actually 3D, so I'm showing you transaxial coronal and sagittal slices of a 3D volume of a phantom called the XCAT phantom. And we extracted 8 by 8 by 8 patches from this phantom, just this one 3D phantom. So this is my number of training examples here is one image and all of the 8 by 8 by 8 patches from that. And so my transform that I'm learning is 8 cubed by 8 cubed. Not too big. I can still easily do SVDs of 512 by 512 matrices. It's a little bit hard to show you what that transform looks like in a meaningful way. So what I've done is I've extracted pieces of the transform and reshaped them into 8 by 8 images and shown you here. All right, and so you can see it's learning things that look, related to finite differences at different scales. This looks to me like a second order finite difference, kind of a -1 to -1 along, at some angle. All right, so that's learning a unitary transform from a single training data, but keep in mind there's a lot of patches. There's roughly 512 cubed patches in this training data. I don't know, it's actually not that many slices. 512 squared by probably 100 slices here in training data. So that's a lot of patches to learn from. So now we've learned that transform from training data. How would we use it as a regularizer? Just the way I showed you earlier when we had handcrafted transforms. So we have a cost function that involves a data fit term and a regularizer, where the regularizer is asking that patches extracted from the image we're trying to reconstruct should be should be sparse with respect to that population learned transform. And here I wrote down a 0 norm because that's what we used in the paper, but you could equally well use a 1 norm because this problem is now a convex problem. So if you really want, if you put a 1 norm here, it would be a convex problem. I guess I chose a 0 norm here to be consistent maybe with the way we trained the transform, but I'm not sure it's essential to have that consistency. And we've already discussed that we alternate minimizations. Turns out, just for the results I'm about to show you, we didn't use conjugate gradient. We used another method we developed called the linearized augmented Lagrangian method for the X update. All right, so I'll first show you results with a simulation here. So we learned the transform from some slices of the XCat phantom, and now we're reconstructing 3D different set of slices of the XCat phantom. Here's the true image shown here. This is a low dose simulation. Here's reconstructed using filter back projection, the FDK algorithm. And you can see because of the relatively poor SNR, there's lots of streaks in the image. This image in the bottom left here is reconstructing using edge-preserving regularization. This is what's been in X-ray CT systems in the clinic now since about 2012. So it's called model-based image reconstruction, and those methods used edge-preserving regularization. So you can see that it greatly reduces these streaks. All right, but you notice there's some fine details in the lung that are not, I hope you can see this over Zoom, fine details that are still not fully captured in this edge-preserving reconstruction. Whereas if we reconstruct using a learned transform, you can see there's further reduction in the noise compared to this, I hope, and these fine details in the lung are better preserved. And I'm sure that the reason for this is that edge-preserving regularization is just using patches of size 1 by 2, right? It's just using neighboring pixels, whereas this ultra is now using, excuse me, this learned transform approach is using, 8 by 8 by 8 patches. So a lot more context for evaluating or exploiting sparsity. These are air images showing the extensive amount of noise in filter back projection, greatly reduced noise in the edge preserving regularization, and then further reduction once we bring in the learned transform. To put some numbers on it here, here's the filter back projection. Let's just look at the higher dose level here. With this is root mean squared error in Hounsfield units, which are the relevant unit in CT. So you cut the amount of noise, roughly in half when you go from FDK to edge preserving regularization, and that's why that's been used clinically so much. In terms of root mean squared error, you don't see a huge improvement when you start using the sparsifying transforms, but that's because root mean squared error is evaluated over the entire image, and or at least the entire support of this image. And there's a lot of uniform regions in this image. What you really care about is those improvements in the fine details that I was showing you in this image so far. And those improvements don't really show up well in our root mean squared error criterion. Now, it's been said that education is the process of telling smaller and smaller lies. So I need to tell you what I actually showed you in this image was not a single sparsifying transform, but a set of a few sparsifying transforms. It's a union of learned transforms. And you can see that leads to additional reduction in the root mean squared error. That's why I showed you those pictures. And this is the actual learning process that we used. So instead of just learning a single sparsifying transform, we learned a set of, I think it was 5 sparsifying transforms. So for each patch, we are trying all 5 sparsifying transforms and finding the one that best sparsifies that patch. And so, and we're doing that over the collection of all patches. And so we're sort of finding this set of 5 transforms that collectively can best sparsify all the patches extracted from these images. That's called a union of learned transforms. This joint work with Sai Ravishankar, who's now a professor at Michigan State University. And we have efficient alternating minimization algorithms for solving this problem. And in case you're curious, this is what the different transforms sort of look like. And if you take the training data and see for each patch, which sparsifying transform was the one that was selected for that patch, you can see they sort of cluster according to different regions. I wouldn't consider this a a real clustering or segmentation method, but you can see there's some coherence to it. It's not random. Different regions in the images are being better transformed by different sparsifying transforms. In fact, you see here, this particular class tends to have edges at this particular orientation, and you can see that sparsifying transform has a lot of learned transform components that would seem to do a good job of sort of sparsifying things with edges at those angles. Now, there's a question of how we chose 5, and I don't remember how we chose 5. That's a great question. I will have to ask my collaborators, sorry. And the question was also asked, did we do anything to encourage diversity of the learned transforms? And we did not do anything to do that I recall. The cost function itself does not have any such encouragement in it. No explicit encouragement, but I think there is no benefit to learning the same transform twice, right? Because that wouldn't, if you happen to have 2 transforms that were exactly the same, I am sure I could immediately reduce the cost function by taking one of those and changing it to something else, because some of the patches would then be better sparsified by that modified transform, and the original ones that were happy with the original transform would stay where they are. So I'm not sure that there's any need to encourage diversity. If it were doing a synthesis version with dictionaries, I think we would have that need, but I'm not sure we have that need here to encourage diversity. But the question of how many transforms is an excellent one, and I will have to punt on that for now. I should actually make a note of that. All right. Now, somebody might be thinking at this point, but wait, you learned on XCAT and you applied to XCAT, it's different slices, but it's still the same kind of structures. XCAT Phantom did come from an actual patient, by the way, so it's anthropomorphic in that sense. We've also applied this to real data, and here's one example that came from that special issue of the TMI. This is a chest CT scan, reconstructed with filtered back projection here, with edge-preserving regularization, which again is essentially what's being used, has been used clinically in scanners, and then reconstructed with this union-learning-find transforms. Of course, we don't know the ground truth here, so I can't give you any numbers. I will call your attention, let's see here. I was presenting this once to an NIBIB panel, and somebody was asking about some of these subtle white and dark structures in here, and there was a radiologist in the room who could confirm that he thought that these were real properties of some disorder of the liver or whatever, that he thought he could better see here than in either of these 2 images. But that's an anecdotal, sample size of 1 observation. You do see some finer details in the lungs here, at least I can see on my monitor, that you can't see as well here. So it's kind of interesting. Despite training this transform or union of transforms on XCAT Phantom, it still has some benefit, it appears, for real data as well. Of course, we could also learn the transform from high quality patient data as well. We just didn't bother to do that. All right, so that was one example using a population approach with a patch-based regularizer and a transform of the patches. My next example is a patient-adaptive approach where we're learning a dictionary instead of a transform. So this is a synthesis model now. So patient-adaptive, again patch-based synthesis approach. So here, there's no training data. We're going to try to learn the dictionary as we reconstruct the image. This again is joint work with Sai Ravi Shankar at Michigan State. So we have a cost function as always with a data term, but now we have a more complicated regularizer. Earlier I showed you I basically showed you the same regularizer before, where we said we want the patches extracted from the image to be, able to be represented sparsely as linear combinations to some dictionary. But earlier I said I knew the dictionary. Now I'm learning the dictionary as I do the reconstruction. So for each candidate image, I'm going to see how well I can sparsify that candidate image with respect to some dictionary. So this is a much harder optimization problem. I will mention that this is now non-convex for 3 reasons. First of all, I put a 0 norm here. Second of all, the constraint that we put on the dictionary is that the norm of each column of the dictionary, each atom in the dictionary, is unit norm, and the hypersphere constraint, that's a non-convex set. And then finally, we have a product of two optimization variables, D and the sparse coefficients here. So all three of those things make this a non-convex problem. But again, we tackle it with alternating minimization, updating the image, the dictionary, and the sparse coefficients. The sparse coefficients are just hard thresholding. The dictionary update takes a little bit of work, and we use something called sum of outer products dictionary learning that Sai Ravi Shankar developed for that. It basically updates one atom of the dictionary at a time, and then the corresponding coefficients of that atom, and it alternates through all the atoms and coefficients. And then again, we have a quadratic update for X. Now, I saw another question came in. Does this relate to the Gaussian mixture model view Shapiro-Mollet or Sure-guided denoising Morel et al.? And the answer is I don't know. That's an excellent question. I'll have to look at that offline. I assume that question came back here. That question was probably back here with the learn set of transforms. And boy, whether that's related to a Gauss model, I mean, there is a square here. So I guess if I exponentiate this, maybe it turns out to be related to Gaussian mixture model, but I don't know. I will have to look into those references afterwards. Okay, thanks for the pointer. Okay, so again, despite the non-convexity, this alternating minimization algorithm does have some, let's say, local convergence theory associated with it. Better than nothing, I'll say that. Sorry, Sai, if you were hoping I'd say something stronger than that. Okay, so here it is applied to real data, real MRI data. Again, there's no training data here, right? We're learning the dictionary as we do reconstruction. So this is a phantom where we reconstruct with a fully sampled data, so you can see what it really looks like, the phantom. The ripples that you maybe can see in this image are due to the fact that we have finite case space in MRI, so there's a Gibbs artifacts that are always present there. If you collect only retrospectively undersample this, so we fully sample the center of case space and then undersample the higher frequencies by a factor of 2.5 and reconstruct that, then you get all this ringing and aliasing in the direction along which you've undersampled. And then this is the image reconstructed by the cost function that I showed you. As we're reconstructing, we're learning a dictionary, and it's an overcomplete dictionary. We initialize that dictionary with a combination of the DCT and just random atoms. And then as the image is being reconstructed, it's learning a complex dictionary. As the question came up earlier, MRI images are complex. So this is we're showing you both the real and the imaginary part of the image, and you can see it's retained some atoms that seem to be kind of DCT-like, and then it's learned other atoms that a little harder for me, frankly, to explain what they are. Maybe it's easier to interpret transforms that is dictionary atoms. I'm not sure, but anyway, these are the components that it's learned. Of course, it occurs to me as I'm looking at this that some of these atoms may never be used in our sparse model, so it'd be more interesting to actually just show you which of the atoms that are most frequently learned. I'm going to make a note to myself to look at that later, because I think that would be interesting to see which of the atoms that are used the most frequently out of that. Now, there's two ways you might set this up. If I go back to the cost function, you might put a 0 norm here or a 1 norm here. It's going to be non-convex either way, but you have the choice. And here's what we found empirically, that if we use a 1 norm, the algorithm, for whatever reason, converges faster initially. Whereas if we use a 0 norm, it converges slower initially, but eventually reaches a higher PSNR in the reconstructed image. So it's, in hindsight, it would be natural to think, well, maybe we should start with a 1 norm and at some point switch or do graduated non-convexity or something towards a 0 norm. And this difference is, a 1 dB or whatever difference can be useful actually in MRI, or probably other problems as well. There's code for reproducing this if you're interested. And since the 0 norm gets better results and the problem's non-convex anyway, everything I'm going to show you is pretty much with the 0 norm here. Now you might be thinking, that phantom image is very simple. Convince me on some more interesting data. And in our original submission of this paper, we had, 4 or 5 cases, and the reviewers asked for even more. And so you can see we've ended up with 7 cases here in the final version. And for each of these images, we tried different sampling patterns with different acceleration factors. The zero field reconstructions, of course, are horrible in terms of their PSNR. Sparse MRI, that's compressed sensing using some combination of wavelets and or total variation. I forget what Pano is, but another method for dealing with undersampled data. Dictionary learning MRI, that was Sai Ravi Shankar's own work that he did in his dissertation, doctoral research before he joined me as a postdoc. So that was his own worst competition in a sense. That method used KSVD to model the patches instead of this aggregate sparsity model that I've been advocating for here. And you can see that using the zero norm with this adaptive dictionary, where you're learning the dictionary from this patient's own case-based data, consistently led to the highest PSNR across all of these different examples with different levels of undersampling and different kinds of anatomy. All right, just to show some error images for, again, the phantom case, you can see that hopefully you can see there's less error in this adaptive approach. Well, this was also an adaptive approach, but it was adaptive using KSVD. For whatever reason, this aggregate sparsity approach led to higher PSNR, and you can see lower errors here. Also, I think it's faster. If I believe there were, yeah, I think we found that the nature of the optimization involved here was faster than using the KSVD approach in DLMRI as well. All right, to pause again. All right, I will resume again. How are we doing here? Half an hour. I think I can do it. All right. I've already mentioned then, with many of these models, you see that once you sort of solve the regularizer update, it leads to a denoiser, and then there's a image-based update. And you could replace the denoiser with your favorite denoiser, and now you may have lost the cost function, but you have an iterative algorithm, and one way to sort of stitch those pieces together are plug-and-play ADM and regularization by denoising. Those were discussed more in last Friday's tutorial, so if you're interested in those, you might want to go back to that. I'm going to move on to deep learning approaches. And I want to say, let's say machine learning approaches first, more broadly here, right? So I've actually been, even though I didn't maybe say it very clearly, I have been discussing some machine learning approaches in the sense that we are learning models, transforms, or dictionaries from patches and training data. Maybe that's shallow machine learning or whatever. I like those approaches because I think the optimization formulations give me some insight into what's going on. They have both the pro and the con that they only, if you use 8x8 patches, you're sort of only able to sort of exploit redundancy or dimensionality reduction of those patches. I think that prevents you from hallucinating any big structures, and we'll talk about that more in a little bit later, but it also maybe limits how good you can do. Oh, I promised a break. So this is the point. We're going to take a 3-minute break here and get your coffee or whatever you need to do. And so I will pick up with the deep learning approaches in 3 minutes here, okay? I don't know if I'm going to pause I think in case this helps with the recording people, I'm going to pause the share for just a minute here, 3 minutes now. All right. Apologize for not remembering to take that break earlier. If we'd been live together, I would have seen your attention spans start to fade. I would have noticed we would needed that break earlier. Okay. I hope you're all back. I'm going to resume now, where I was contrasting two different machine learning families of approaches for image reconstruction. One that's sort of shallow or local learning transforms or dictionaries. And then, of course, the hot topic of the day of training neural networks that are deep learning. A little bit harder to interpret, perhaps. They can use more global prior information, though, because the receptive fields of deep networks are often much larger than the typical patch size used in patch-based methods. They're slow, of course, for training, but maybe, depending on the kind of method used, they might have faster computation compared to the iterative alternating minimization methods that I've been discussing once they're trained. That depends on the details of how you do the deep network. All right, so I'm going to talk at a high level about deep learning approaches to image reconstruction, then I'll dig into a little bit more detail in this last family of methods. All right, so at a high level, the earliest approaches that appeared are what's sometimes called image domain learning, where you take your raw data, you apply your favorite analytical reconstruction method and get typically a lousy image. So in MRI, this would be a zero-filled image reconstructed image, and CT would just be filtered back projection. And then you put through a black box neural network that gives you hopefully an improved image out of that, all right? So you only use the physics once, perhaps, at most, in this initial reconstruction, and then it's just the magic of machine learning after that. This does require, in both CT and MRI, I think, pretty deep networks, because the aliasing patterns in both CT, undersampled CT, and in undersampled MRI are quite widespread across the image. So you need a large receptive field, I think, to correct those aliasing patterns. And the problem with a large receptive field is that it has the possibility of hallucinations. And so I want to highlight for you one talk from a workshop that took place back in January in Sedona, back when we used to be able to get together in person, by a former PhD student of mine who's now a postdoc at MSK in New York, where they're focused on cancer imaging, and they have lots and lots of MRI scans of people with brain tumors. And they trained a deep network of this kind right here to take aliased images from multiple coils, put it through a unit, and de-alias the output. And they gave it lots and lots of examples of brain tumors of different kinds. And then they applied it to a particularly rare malignant brain tumor that I won't try to pronounce the name of here. Here's the reference data. They retrospectively undersampled the data by a factor of 4, so 4-fold acceleration. And when they put that undersampled data through a classical, let's call it classical now, compressed sensing reconstruction, they got an image that was pretty good agreement with the ground truth. But when they put that same case-based data through their deep learning method, they got an image where the tumor was virtually obliterated. So this is hallucinating, not a tumor, it's hallucinating more or less normal brain structure where there really should be a tumor there. And I think that's a caveat of image domain methods that one needs to be aware of. So this is a super fast reconstruction method after it's trained compared to the iterative algorithm needed for sparse sense. But a factor 4 acceleration is not particularly aggressive, and to lose that kind of key information because that tumor was so rare that it wasn't appearing in their training case is a cautionary note. Generate a lot of discussion at that workshop. There are other variations of image domain neural networks learning. You could use the output of the neural network as a sort of prior that you then go back and revisit the data. And now this is a quadratic optimization problem you could solve hopefully relatively quickly. And maybe, if there's, they didn't try that method on this case. It'd be interesting to see whether the case-based data itself would be able to speak loudly enough to overcome the missing feature in the neural network image. There's other variations on that I won't discuss. There's also deep learning approaches that work in the case space or the measurement domain. So you take your corrupted, undersampled, noisy, whatever it is, raw data, you put it through a network that tries to complete the data or denoise the data, and then put it through a maybe non-iterative simple reconstruction method. and there are a variety of methods of that, that kind. They have some advantages. There's at least some that are database free. They're sort of patient-specific adaptation. They just use the redundancy, if you will, in parallel MRI across multiple coils to sort of train the neural network on a patient-by-patient basis, which is kind of attractive. I think it's probably hard to capture local features of an image in sinogram space or in case space. So I think that might be one drawback, limitation of those methods. There are a few ambitious people who've tried to directly learn a transform that takes you from the raw data to the reconstructed images. I've seen this now in MRI, a method called AutoMap, and also in CT and PET inspect. And in every single case, they've only been applied to relatively small data set sizes because the relationship between data and the reconstructed image is not very convolutional. So you typically need some stages at least to fully connect the networks here, which are very large. And you're trying to basically learn the physics. They might argue otherwise, but you're essentially trying to learn the Fourier transform there. And so people who have worked on this in those various modalities typically have been limited to 2D modest size images, and it's pretty difficult to generalize this to 3D images of sizes of greatest interest. All right, and so now where I'll spend most of my time is where I think most of the field has also evolved to, and if you saw Friday's tutorial, you would have seen this theme as well, which is neural network methods that combine sort of physics and the denoising capability of some kind of adaptive model. All right, so you maybe initially do an analytical reconstruction, you get initial image, then you put that through a neural network to denoise it, then go back and revisit the physics and keep doing that over and over. And there's many different ways of doing this. So it takes more computation, that's the drawback. It takes more computation than just a one-pass black box approach, but I think has the benefit of having the probably best possible image quality, and that was borne out in that competition as well, the fast MRI competition, whereas those kind of methods that were at the top of the leaderboard. And I'd say they're a little bit more interpretable as well, because this box here is just doing denoising, so you kind of probe it with different kind of inputs to see what behavior it has. And so part of the reason I spent so much time at the beginning on different algorithms is that basically every algorithm that I described and more have been unrolled into iterative neural network methods, whether it's ISTA, LISTA, ADMM, and so on, alternating minimization algorithms, and so on. Every one of those people have, and more, have replaced the denoising step with some kind of neural network-based denoiser there. And in fact, this is happening enough that there are now a couple survey papers about these families of unrolled or unfolded algorithms. Now, I'm going to come back to those in a minute, but I want to talk about a couple of other high-level approaches that you might think about for machine learning influencing image reconstruction. So a hot topic in CNNs right now is, for a while anyway, has been like adversarial networks or generative models, autoencoders, and so on, where you have some kind of mapping between a low-dimensional latent parameter and the image, let's say, of interest to you. All right, so remember again, in undersampled data, we need some form of dimensionality reduction, and most of the forms I've been describing are sort of linear in some sense. You have a dictionary, linear combination of atoms, or a transform, a matrix vector multiplication there. There's nonlinearity from the sparsity, but the sort of key piece of it, the dictionary transform, is linear. This is inherently nonlinear now. You have a nonlinear model relating your latent parameters, think of those as your sort of sparse coefficients, if you will, into your image. And so if you believe you have a good model that can generate images of interest from a low-dimensional parameter space, you can do this in synthesis form, where you find the latent parameters that synthesize images that best fits with the case-based data. And in this form, you don't really need regularization because you've already reduced degrees of freedom. Typically, this latent parameter would be many few parameters than your number of pixels in your image. The caveat with this is that it really does mean you're going to end up with an image in the range of your generator. And if your generator is not fully representative of your rare tumor or whatever, you're going to miss it. I think a little bit more safe form might be to turn this into a regularizer, where you say, I want an image that agrees with my data, but my image is also reasonably close to an image that could be generated by my generator, but I don't insist on equality there, and there's a regularization parameter that lets us adjust how much we believe the data and how much we believe the generator. But now it's a more complicated minimization problem, but it might be more robust to imperfections in the encoder. And just to give a graphical illustration of these encoders, here's two-dimensional representation of handwritten digits from some recent work where you can kind of generate lots and lots of handwritten digits of images of size, you know, whatever this is, on the order of 600 or something pixels from just two parameters. Now it's a little bit hard to find the 4s in here. They're sort of blurred between the 7s and the 9s, but so maybe 2 is a little bit too low of dimensionality, but you get the idea that there's the potential for dimensionality reduction here. But there's caveats as well. You know, here's some images synthesized, face images synthesized from what I think it was Google described as setting a new milestone in visual quality a couple of years ago. And if you zoom in on one of these images, you see some blemishes. And this might be fine for computer graphics, games, or whatever. But if that is a tumor that's either hallucinated or missed in a medical scan, that is a potential concern. So people have also explicitly put CNNs in a form of regularizer. The modal approach kind of does that, where you take the difference between X and a denoised version of X and essentially regularize that. And this approach has some benefits I'll let you read about in the references. So in general, things one has to be aware of when using neural network methods is that, at least traditionally, they need a lot of training data, although every limitation I mentioned, somebody's working on trying to overcome it, and self-supervised approaches are one attempt to overcome limited training data. The loss functions for training neural networks are very non-convex, so it's hard to get, you know, say something about global minimizers, but people are working on that as well. And so on. There's a lot of choices to make. It used to be in the early days of regularization, everybody would ask, how did you choose your regularization parameter? And that was just a single parameter. Now you have zillions of choices to make in terms of architectures and parameters when you design a neural network. The loss functions that we use to train neural networks have been things like mean squared error, SIAM or whatever, maybe some image quality related things, but it's unclear how those metrics really relate to clinical tasks, although the Fast MRI challenge had pretty good agreement between SSIM, that structural similarity metric, and the radiologist's preference for the image. So there's some hope there, but I think there still is a research opportunity to try to make metrics that are more closely related to clinical tasks. Lots of questions about generalizability, memory, and so on. I'm going to skip this example. And I'm going to end with my current favorite unrolled loop algorithm from my former postdoc, Il-Young Chun, now at the University of Hawaii. Again, to ease into this, remind you, I was looking at these convolutional regularizers earlier, where we want an image that fits the data, but that when we convolve it with some filters, produces sparse outputs. And the iterative algorithm for that involved alternating between soft thresholding and then a quadratic cost function. And if you solve analytically for the sparse coefficients and plug back in and simplify, you get what I mentioned earlier, that there's a filtering, soft thresholding, and a conjugate filtering, or adjoint filtering step there. And then finally, a quadratic problem that needs to be solved. And we might want to majorize that quadratic problem because it's so large. And that leads to an algorithm that we've called momentum net that has Nesterov like momentum term, or heavy ball method like momentum term in it. We replace this denoiser with a learned denoiser that he calls an image refiner. And then finally, there's an image update that involves the physics of the data, so the gradient of the smooth part of the data term. Smooth part of the cost function. And then you repeat this. That's the unrolled part. So this is kind of one iteration of the algorithm written out graphically like you have in a network. But it's using both the previous iteration and the one before that in this momentum term. And the image mappers, the denoisers that we use here are shallow. They're just basically a set of filters, thresholds, and then filters again. because we think this has less risk of overfitting or hallucinating undesirable image features. It's easier to train that way as well. By using momentum, I'll show you that it actually leads to fewer layers or outer iterations of outer iterations that are needed. And we have some convergence theory for this method, actually, which is relatively rare in the unrolled loop methods family of things. So under certain assumptions on the learned regularizers, if you were to keep doing more and more unrollings, we would actually converge to something. And there's a paper on Archive that describes the details of that. Here's a plot that shows the benefit of using extrapolation. So this is an older unrolled net we had. There was alternating minimization of block coordinate descent. Let's focus on the momentum net here. The black curve shows the root mean squared error in a CT reconstruction problem as a function of reconstruction time. If we don't use the momentum or extrapolation, and if we do, and you can see there's a significant reconduction in the time involved if we use that momentum. So I think that's helpful. And then finally, some reconstructed images, and there's too many to show here, but I'll just focus on, let's say, the top row of these here. So some of these you actually have seen before. So this is the ground truth, filter back projection with all the streaks, and then edge preserving regularization of the kind that's used in the clinic. An approach where we learn some filters offline and then applied it for reconstruction. And then finally, this deep network momentum net approach. And you notice there's a big drop in root mean squared error when we go from learning filters from training data versus this sort of learning it as part of this unrolled loop algorithm. And more importantly to me, there's this structure here in the ribs that our previous methods were always kind of smearing out. You know, we were able to reduce the root mean squared error, but these structures were kind of smeared out. And finally, for whatever reason, the learned filters in this momentum net have been able to sort that out and get some structures that much better agree with what the ground truth looks like here, while preserving, you know, fine details in the lungs that are not very well visible here and so on. So I'm pretty excited about this. This is probably the best images that for CT that have come out of my group, and we'll be applying this to MRI pretty soon. All right, so skip dynamic reconstruction. You know what, I'm going to skip this as well because I am really approaching the 2-hour point here. Oh, I just mentioned one more thing. So I have focused on the image reconstruction problem, but I want to mention that machine learning is also has great potential opportunity for the acquisition problem in MRI. You have to choose which case-based samples to record in undersampled reconstructions. And I think there's now starting to appear a variety of methods for trying to use training data to choose the sampling. So we can use machine learning both on the acquisition side as the reconstruction side. And in fact, there are some groups now starting to look at trying to optimize those jointly, which I think is quite interesting work. Optimize together the sampling pattern and the reconstruction algorithm. All right, so I think I will leave it at that with thank all of the members of my group, some postdocs, especially these individuals named here who had a role in contributing to the results that I've shown you along the way. I want to remind you again, the talk is available online at this URL. Some Julia code is here. Thank you for your attention. I'll be happy to take questions now. Whew. You know what I'll do? We're a small enough group. I think I'm just going to, let's see if I can unmute everybody. That's risky, but why not? Let's see here. I guess I'm just going to have, I'll just click you one at a time here. So that if anybody wants to chime in with a question, you are welcome to do so. All right, I hear somebody warming up the microphone. Hello.
Hi, Jeff. Just want to thank you for your wonderful tutorial.
Thanks, Bo. Appreciate it very much.
What's the future for the machine learning-based approach? Since you have shown that so many algorithms has been enrolled, yeah, and so many model has been coupled with the algorithms. So what you envision the future of this model-based or learning-based or combined?
That's a great question. So, I don't know. I don't exactly know the answer, but I certainly think that generalization is still an important question, right? And I think people are starting to work on that, right? That I'm sorry, somebody's mowing the lawn right outside my window, so I'm sorry if there's a bunch of background noise now. MRI in particular has so many different ways that you can acquire the data, right? Different coil configurations, different samples and case space, different echo times and contrast. And the idea that we could train different networks or whatever for every single application is kind of overwhelming. There's just way too many options. And so developing networks or methods that somehow can work for in a plug and play kind of way for many, many different kinds of scans, I would think would be important for making this feasible in the clinic. I should mention, by the way, in CT, there are already FDA approved deep learning based methods for CT image reconstruction. I think they're pretty much denoising methods. I think they're doing filter back projection followed by denoising. It's proprietary. I don't know the details, but CT doesn't have so many options, right? You can change the KVP and the dose in MA. There's not nearly as many options as in MRI, so it's probably pretty feasible for them to develop a network that can handle a reasonable range of certain kinds of scans in CT. To make this, as far as I know, there's no FDA-approved deep learning methods for MRI yet. It took 10 years from compressed sensing to go from paper to, you know, FDA-approved products. It probably won't take that long for CT with deep learning, or excuse me, it took much less time than that for CT to go from deep learning sort of craze in the field to FDA-approved product. But if you know anything about MRI that's already happening, let me know. But I'm not aware of any clinical methods for MRI yet, and I think there's some significant practical challenges there.
Yeah. Thanks, Jeff.
Yep. Thank you, Bo.
This is Greg Buzzard. So in one of the, sorry about my dog. There's so many dogs.
It's a Zoom world.
It's life at home. You had, it looked like in the last thing you were showing, you had 100 layers. I wasn't totally sure if that was like LYR. I wasn't sure if that was 100 layers.
Let me see. This is time in seconds. Let me see.
Oh, right there. And the E and capital N's of LYR.
Yeah, that's 100. That's right. So this is not deep learning for the purpose of speeding things up. This is the purposes of getting better image quality in a, I don't remember the yeah, I mean this is 8-fold sparsification CT. That's pretty aggressive reduction in number of views. So yeah, that's a lot. I totally agree. That's way more iterations than we would have used in model-based reconstruction. You know, this edge-preserving regularization was probably, you know, 10, 20 iterations of somehow, you know, ordered subsets algorithm or whatever. So yes, that is a lot. And I don't think, let me see here. That's let's look at the final number here, 20.9. I'd have to check with Il Yang, but I can't count how many points here to see whether, oh no, I'm sorry, it's probably this, yeah, it's probably those 100 points right there, because it would be this algorithm right there. So it doesn't look like we could have stopped a lot earlier and got that sort of, you know, it's plateaued here, maybe 80 or so iterations. Yep. And maybe if we used a little bit deeper network per layer, right? So we're only using what, filter, threshold, filter here, right? And so maybe we could use a little bit deeper network per layer and then not have to use so many layers or outer iterations. Explore that. What do you think?
No, I'm just interested. I mean, because I guess like one of the problems with deep networks, as you were pointing out, is the possibility for hallucination.
Right.
But the fact that you have this kind of unrolled structure helps prevent that, I guess, maybe.
I think so. I think it really does help. So even though it's 100, don't think of it as like 100 layers of deep network, right? We keep revisiting the physics every single iteration.
Right. Yeah.
Not too far away from what the sinogram data itself has to say here. And that's intuition and sort of gut feeling. I don't have a proof of that. It would be nice to have some analysis of sort of quantifying how far could it. could it go, right? And
right. And the example where it missed that tumor was pretty disturbing.
yes, I know. That's why it generated a lot of discussion about absolutely. And this is, you know, you could imagine if this had been done at a group where they don't have very many tumors, but this is a, you know, a brain tumor specialized place. So they had a lot of brain tumors.
Well, I'm also curious there about like what the analytic reconstruction would look like.
Oh, that would be interesting to see. Full acceleration. Yeah, that I agree. That would be very interesting to see. Obviously, not as good as this.
Right.
Because that analytical reconstruction, of course, was the input to this
right.
method. That's
yeah, exactly. And you can kind of still see where the tumors would be in the DL reconstruction, but it just kind of blurred them out.
Yeah, with the hindsight of seeing the images on the left, I think if I just showed you the image on the right, you'd be hard pressed to pick those out.
Yeah, for sure. Yeah, no, of course. Yeah.
Yeah, great questions.
Yeah, so like, I guess that raises a kind of a larger question about like the extent to which we can use just straight neural networks in medical applications. Like as you said, in games it's fine, but
oh, well, okay. If you're going to broaden this to medical applications in general, I think for things like segmentation, registration, other post-processing procedures, I think there's a lot of things one can do. Although, I'm not a specialist in that, so I'm not going to speculate. And of course, you're using a more or less off-the-shelf looking UNet here. You know, there very well may be improvements in image domain learning that can do a better job than this. I don't remember, for example, did they put the complex data in here, or did they put the number of, oh, it says 2 times NC. So actually that tells me right away they put the complex data, the real imaginary parts in here.
Right.
All right, so Hester, is my time is officially up, but I take one more quick question, I guess, and then we'll call it a day, because there's probably somebody's background.
Oh, adventuring time parks.
I'm gonna mute. Let's see here. Oh, that did it. Any last quick question, anybody? All right, I will just go back the last second here to the URL in case you want to, if you didn't get a chance to grab that. End on that slide. Where is it here? There we go. And enjoy the rest of the Imaging Science Conference in this virtual format. Thank you for attending and thank you for your questions.
Thank you.
Yep. Bye-bye, everybody. Stop share. And where is the end broadcast here?